Well, all right then. Here we are again. So, of course, we're meeting online today because spring break is right around the corner. So, what I want to do today is go back and revisit our discussion about the normal distribution and go through it more thoroughly with some new examples. And also, we're going to use the calculators quite a bit today. I've decided that we should save Excel until the next time we meet together in person, which is, of course, a week from Tuesday. In the meantime, though, we can keep going with what we were doing and get all the results that we need with the calculators. So let me just open up some documents here. We have chapter 6, which we're not obviously done with yet. If you recall, we are going to be looking at 3 probability distributions here. One of them is the uniform, which we've done with, the normal, which we're still working on, and then finally exponential, which we may have a look at later on today. So that depends on how far we get. So when we get back next Tuesday, we'll come back and do the Excel commands for these functions. And then possibly we'll start chapter 7. By the way, I do want to mention here too that the second midterm is based on chapters 4 and 5, which we're completely done with. So when we get back, we have to figure out a good time to have the second midterm and the times and dates on which we'll be reviewing, but that can wait till we see each other again. Okay, I just want to make that clear that we're actually very close to having a second midterm as well. The final, as you know, is something that's determined by the administration. It's going to be sometime in, say, mid-May. It's possible that the schedule's already been posted. And for people who are planning on traveling home, let's say flying back to, foreign countries and that type of thing, you might want to take a look at that schedule so that you know what dates to avoid. But anyway, let's get back to this. By the way, I've written up this new document as if I were writing on the blackboard at school instead of written it in a Word document. And of course, the beauty of this is that I was able to save all of this. And I may continue adding to it today, but as we go along, when we're done, I'll be able to post this to Blackboard so you can read through it at your leisure. And if you think you may have missed something today, for example, if you joined late or if you have to leave early or something like that, or if you couldn't be here at all, the recordings of this session will be available. I'm actually going to post it in 2 different places in Blackboard, but also in my own YouTube account because the thing is sometimes, Blackboard is a good system, but, it doesn't have an unlimited amount of storage capacity either. And, videos can be very, very space intensive. So I find that it's safer to have 2 different versions of it available to you. It's the same thing with 2 different copies of it, one on my YouTube account and one on Blackboard, just in case there's a problem. All right, so just a quick reminder here. First, we were looking at the normal distribution, and you can see here's a graph of the normal distribution, and it has that unique bell-shaped curve look to it. And so this is coming from this formula, which actually is used to calculate normal probabilities. So we went over this last time, and so we aren't actually ever going to actually use this formula. We're going to use our calculators or Excel to get the probabilities we need, but they're all based on this function. And you can see it does contain several familiar elements. It has the mean of the distribution. It has the standard deviation. It has pi, which is kind of interesting. And then it has E, which we saw with the Poisson distribution. It's approximately equal to 2.71828. But we're going to use the calculators. And so we've already gotten a little practice with that, but I think it's important to get a little more practice to make sure we really understand how the normal distribution works. So what else do we know about the normal distribution? Well, a few key properties. For one thing, if you notice, it goes off all the way to positive and negative infinity. In other words, there's no upper or lower limit on it, unlike let's say the uniform distribution. And in spite of that, the area under this curve is exactly equal to 1, which is true for all probability distributions. It's also symmetrical about the mean, and you can see that from this graph. So here's our mean. And if you draw a line down the center, the left and the right-hand side are identical to each other. And this is what we mean by symmetrical. And we'll see later on that we can use this property of symmetry to help us calculate probabilities more quickly and easily. Now, we also know that this is a continuous distribution, which means that in principle, there can be an infinite number of different possible values with the normal distribution. And we also know that that the distribution can be characterized by the two values, the mean and the standard deviation. So the mean, if you recall, represents the location of this curve on the normal line. The standard deviation is how spread out it is. All right, so yeah, you can see here they've got a few examples. These are all different normal distributions. They have the same standard deviation, you can tell because of the shape, but they all have different means or locations. Here, they're showing you a case where they have two normal distributions. They have the same mean because they're in the same location. But the very tall one has a low standard deviation, and the very short one has a very high standard deviation because it's more spread out. So that's what those two numbers are telling us. Once we know those two numbers, we can calculate any probability that we need. You might also remember that there's a special case called the standard normal distribution, which is the one unique case where the mean is 0 and the standard deviation is 1. We're going to get a lot of use out of that one. And also, just as an aside, the letter Z is used for the standard normal distribution. X is used in every other case. So, up to this point, we've been using the letter X to represent random variables. And that's still the case here, except for the standard normal, where we use the Z instead, just to make it clear that this is the standard normal. And in fact, that's where the name Z-score comes from. Okay, we'll be doing some of those later on today. The fact that is a value under the standard normal curve is what makes it a Z-score. All right, great. Now, we're going to start with an example, just in case we didn't get enough practice the other day. Imagine myself showing you that we have the standard normal distribution, and that implies that the mean is 0 and the standard deviation is 1. I want to know the probability that Z falls somewhere between 1 and 2. And you can see in the shaded region, this is what we're looking for. So how does one do this with a calculator? So if you remember, the function we need is called normal CDF. It's found in the menu second vars. And use number 2, normal CDF. And when you get there, you'll recall that it asks you for 4 things: the lower limit, the upper limit, the mean, and the standard deviation. Okay. So now, since this is the standard normal distribution, we know to make the mean 0 and the standard deviation equal to 1. The lower and the upper limit are these two numbers. So with continuous distributions, we only calculate probabilities based on an interval rather than individual probabilities. So we always have a lower limit to our interval, and we always have an upper limit. And sometimes, as you saw last time, that upper or lower limit might be either positive or negative infinity. So in this case, though, the limits are 1 and 2. And we know that the mean is 0 and the standard deviation is 1. If you type that all into your calculator, you should get approximately 0.1359. Right? So that is rounded to 4 places. And so you can see I put it up here in the graph. And that means that this section represents 13.59% of the total area under the curve, which is 1. So that probability is 0.1359. All right, so that's not too difficult. Now, here's an interesting side note. Because of the symmetry of this distribution, I put it up here in the upper right-hand corner, just so you can see them side by side. If instead I was asking for the probability that Z is between -2 and +1, well, you can see it has to be the same probability because the two areas are identical to each other. In other words, think of them as mirror images of each other with respect to the mean of 0. So in a case like that, I don't really need to use the calculator because I already know what that probability will be. So when this happens, you might you may as well take advantage of it. So these two, of course, have to be the same number because of the symmetry of the distribution. So the symmetry will be very helpful as we go through and study the normal distribution. Well, if that's the case, let's try this one. Another standard normal distribution problem. We're trying to figure out the probability that z is greater than or equal to 1.5. Now, this one is a little different because the upper limit is infinity. Not a constant, not a real number, but infinity. That becomes our upper limit. And so the question is, how do we enter infinity into the calculator? So remember from last time, the method for doing this is to type second comma 99, which means that what you're really entering is this, E99, which is the calculator's way of saying 1.0 times 10 to the 99th power. It's a gigantic positive number. It's not infinity, but it's as close as the calculator can get. So keep the mean at 0 and the standard deviation at 1, type in those numbers, and you should get, rounded to 4 places, 0.0668, or 6.68% of the total. All right. Now, I do want to point out here that since this is the standard normal distribution, that 1.5, let me write it a little bigger over here so you can see it better, can be interpreted as the mean plus 1.5 standard deviations. Or think of it as 1.5 standard deviations above the mean. All right, so in other words, that 1.5 can be interpreted as 1.5 standard deviations above the mean. So when we're dealing with the standard normal distribution, all the numbers you see across there are all telling us how many standard deviations we are either above or below the mean. 0, of course, means the mean itself. Now, again, taking advantage of this wonderful symmetry property, if I now ask for the probability that z is less than or equal to negative 1.5, you can certainly go into your calculator and do it, but you already know in advance that it's going to equal 0.0668 because these two tails have to have the same area or probability. Okay. I actually drew it right down here. You can see that the two give me the same results, but let's just do it anyway, just to get some practice, because we want to make sure we understand how to enter negative infinity here. So it's basically the same thing as positive infinity, except for the addition of the negative key. So of negative second comma 99, that will be replaced with this expression. And that in turn is the same thing as saying negative 1 times 10 to the 99th power. So that's as close as negative infinity as we can get on this calculator. The upper limit would be the negative 1.5. And once again, this number can be interpreted as the mean minus 1.5 standard deviations. Okay, so as we predicted, if you type in all those numbers, you'll end up with 0.0668. So in other words, we were able to do this directly with the calculator, or by recognizing the symmetry of these two areas, we know that they must have the same probability. Now there's more though. There's another way we can take advantage of the properties of the normal distribution. I've got these two tails. What about the area in the middle? In other words, what's the probability of being between negative 1.5 and positive 1.5? Or in other words, within 1.5 standard deviations of the mean. Okay, well, again, we can go directly to the calculator. Okay, hold on. Anyway, so that means lower and upper, or we're looking for a lower limit of negative 1.5 and upper limit of 1.5. The mean is 0, the standard deviation is 1. Now we end up with 0.8664. As you can see over here, I've put it over here. So we know the areas of the two tails and we know the area in between. If you notice, these three have to add up to 1. So that means one way I could have solved for this without using the calculator is to say, well, that area in the middle must be equal to 1 minus the area of the two shaded regions because the three of them have to add up to 1. So I could have done it this way down here, 1 minus the probability of z is greater than or equal to 1.5 minus the probability that z is less than or equal to minus 1.5. And of course, we already know that those are each equal to 0.0668. And if you do that algebraically, you'll see that you do end up with 0.8664. Okay. So just be, you should always be aware of these ways of, we can calculate these areas sometimes simply with our knowledge of the properties of the normal distribution. Now, here's another one. I think we mentioned this last time. What if I just simply asked for the probability that z is greater than or equal to 0? Meaning that we're in the upper half of the distribution. Well, since the total area is 1, that indicates that this area must be a half. Or, in other words, the probability of being above the mean is just 1/2. And that in turn implies that the probability of being below the mean is also a half, because the two of them have to add up to 1. Okay, in fact, I'll add this right here. Because that covers the entire area under the curve. All right, so now we want to try something different. Up to this point, all these problems were all based on the standard normal distribution. What happens if we have a different situation on our hands? Now, we did use this example last time where we had scores on an exam that were normally distributed, but the mean is 80 and the standard deviation is 5. So a couple of things to note here. First, we're using X now, the normal. We usually use X for random variables, but remember, Z is reserved for the special case of the standard normal distribution. If they're going to give you a normal distribution without it being standard normal, you have to be told what the mean and standard deviation are. So here they're telling us that the mean of these exams, the mean score is 80, and the standard deviation is 5. So imagine yourself being asked this question: what's the probability of getting 70 or below on this test? Okay, interesting question. So we'll start by going to our calculator, and we're going to use, again, normal CDF. What's going to change, though, is that the mean and the standard deviation have to be changed from 0 and 1 to 80 and 5. Now, after you get used to using the standard normal distribution several times in a row, it's easy to forget about this little detail. You now suddenly have to change the mean and the standard deviation. It's easy to forget. So if that happens to you, just remember, when you get your answer, it'll probably be either extremely large, like 0.999999, or extremely small, like 0.00000 something. That would be a sign to you that something's not right. It's not impossible, but not likely for those to be the right answer. So double check, make sure you have the right mean and standard deviation, and chances are that's where you made the mistake. So assuming that we've done this correctly, we're going to have an interval from -infinity up to 70 with a mean of 80 and a standard deviation of 5. So once you plug that into your calculator for a second and see what you get, well, you can see what it's supposed to be, but once you plug those in, just to get some practice, and you should get 0.0227. And a quick reminder, up in the top here, I've pointed out that because the mean is 80 and the standard deviation is 5, 70 represents being 2 standard deviations below the mean. So if you notice, that probability is quite small, isn't it? Yes, it is. So what this is reminding us is that the vast majority of this distribution, well, 2 standard deviations of the mean. Not that the area outside of that range is 0, but it's getting very close. So the overwhelming majority of the area is within 2 standard deviations of the mean. So in this case, because 70 is 2 standard deviations below the mean, the chances of getting a 70 or worse is pretty small. Now let's flip this around, and you probably can see where this is going. Let's try the other side of the distribution. Let's see what the probability is of getting more than 90 or 90 or more. And this in turn is actually the mean plus 2 standard deviations. So once again, you type in your numbers. The upper limit is infinity, which we know is 2nd comma 99. And nobody should be surprised to see that we end up with 0.0227 again because of the symmetry of the distribution. So in other words, down here, I've shown that 70 or below, 90 or above represent the same areas of under the curve. They must therefore have the same probabilities. 0.0227. And it says, yes, here we go, right here. Wow, man, that symmetry is powerful, isn't it? If only other parts of life were symmetrical, that would make things very nice. Oh, and one more thing, I thought I'd sneak this in just to also help you understand the properties. What if I now asked you, so we just concluded, let's go back to the top for a second. Probability of X being less or equal to 70 is 0.0227, right? That means that if I need to know this, it will equal 1 minus 0.0227, and that will equal 0.9773. Why is that? Because the total area under the curve is equal to 1. How do you like that? So there's another way we can take advantage of the properties of this normal distribution. Okay, so there's no symmetry here, but we do know that whatever's going on in the left tail is 1 minus what's going on in the right tail. Wow, okay. All right, now here's a formula. I'm pretty sure we never got to this part. This formula shows me that it's possible to take any normal random variable and convert it into the equivalent standard normal random variable. And the result of this calculation is what's called a z-score. And we've already seen z-scores in the earlier chapters, but without a lot of the background that we're seeing here. So why is this even necessary? Well, it turns out that you know that there's an infinite number of normal distributions that are possible because we can have an infinite number of different means and standard deviations. Before the invention of calculators and computers, the way people calculated normal probabilities was to use tables. Okay, mathematicians sat down and they drew out these tables of probabilities. The only problem is you can't realistically have a separate table for each case because then there would need to be an infinite number of them. So if you look in the back of any statistics book, you'll see a table for normal probabilities, and you'll see that it's also based on the standard normal distribution. Why is that the only one that's really needed? Because in principle, I can take any other normal distribution and convert it to the standard normal form with this simple formula. So we're assuming here that X is some normal random variable with a mean of mu and a standard deviation of sigma. And by taking x, subtracting the mean, dividing by the standard deviation, the result is what we call a z-score. All right, so we're going to do a couple of examples of this right now. Let's say we want to know the probability that for the same exam that we've been looking at, the probability of getting, what is the probability of getting a score between 75 and 85? So I'd like to remind you here that that means we're looking for the probability of being within one standard deviation of the mean. All right, so now, of course, we can always go ahead to our calculator. We'll have no trouble doing it directly because you can see that we have the lower limit of 75, the upper limit is 85, the mean is 80, and the standard deviation is 5. So if you plug in all those numbers, you should get 0.6827. Fine. And of course, you might remember when we're doing the empirical rule, they told us that the probability of being within one standard deviation of the mean is approximately 68%. And then we went ahead on the last class and we showed the exact probability is 68.27%. So that's what we're getting here. But if let's say we didn't have calculators and we're required to use a table, what you could have done is use this formula and converted the 75 and the 85 into z-scores by subtracting the mean of 80 and dividing by the standard deviation of 5. And so in other words, the result would be this. And that can be interpreted as being, again, within one standard deviation of the mean. Oh my God, it's the same thing. So if you plug in those numbers into your calculator, now remember, if you're going to do this, be sure to switch the mean and standard deviation back to the standard normal. Okay, don't forget. And you'll see that why, of course, it's the same result because they both mean being within one standard deviation of the mean. In one case, you're using the normal, just standard normal, which means these are z-scores. In the other case, you're using a different normal distribution. Okay. Wow. So now, as if that weren't enough, I've drawn you a little graph here so you can see them side by, well, top to bottom, actually. The one on the top is our original normal distribution, X, with a mean of 80 and a standard deviation of 5. And being within the interval from 75 to 85, as we've seen, has a probability of 0.6827. Down here in the bottom, the standard normal, you can see the same thing is happening because 75 up here corresponds to -1 down here, and 85 here corresponds to 1 down here. So the summary is over here. These two probabilities are the same thing, right? So in other words, it's kind of like switching back and forth between Celsius and Fahrenheit. All you're doing is changing the units, right? The probabilities aren't changing. The curve is the same in both cases. What's different is the units. On the top, these units are points on an exam. On the bottom, these units are referred to as something called standard units. Which means how many standard deviations are we away from the mean? Wow, that was interesting. So in other words, what this is showing us is we have many different ways of calculating these probabilities. And of course, when we get back to school, we'll see that yet another one is using Excel. All right. Now, Excel will be very similar to what the calculator is doing. with some important differences. All right, now we're going to consider the slides have an example for us to work on. And here's how it works. The Greer Tire Company, they have these new steel belted radial tires, and they want to know the details about how long these tires will last. In other words, they need to have a probability distribution, they need to have a mean and a standard deviation. So we're going to assume that they've already determined that the tires, the mileage that you can get out of the tires is normally distributed. The mean is 36,500 miles, and the standard deviation is 5,000 miles. With that being said, the manager wants to know the probability that the number of miles for a given tire is more than 40,000 miles. So let's gather up all this information. Here, you can see that X is the mileage of a tire, and X is normal with a mean of 36,500, and the standard deviation is 5,000. So that means here's what we're trying to find out. All right, here's the graph. Well, I've already spoiled the surprise by showing you the answer, but how would you get this number? So you go back to your friend, the second bars and two normal CDF, and just like before, you can see because this area is in the right tail, the lower limit is that number 40,000. The upper limit is infinity, which we know how to enter now. Don't forget to change the mean and the standard deviation. So if you plug in those numbers, you should get 0.2420 once you round it to 4 places. And you can see that tells me that approximately a quarter of their tires will last at least 40,000 miles. All right, then. Now, they're going to ask us an interesting question here. How many standard deviations above the mean is 40,000? Well, it's not an even amount. It's not 1, it's not 2, it's not 3. How do we figure that out? Good question. And now suddenly we need this formula because let's see what we can do. We have X minus mu over sigma. We know that the mean is 36,500. We know that the standard deviation is 5,000. The X is 40,000 because that's what we're asking about. If you plug that in, you'll see that this is equivalent to a z-score of 0.7. And so that means this number, 40,000, is equivalent to being 0.7 standard deviations above the mean. And that also means that asking the question, what's the probability that X is greater than 40,000 is equivalent to asking the question, what's the probability that Z is greater than or equal to 0.7? And in fact, over here on the side, you'll see that I went back and double checked it. And you can see that by using 0.7 as the lower limit, infinity is the upper limit, with a mean of 0 and a standard deviation of 1, you'll also get 0.2420. Wow, okay. But now, unfortunately, they're going to throw a monkey wrench at us. Oh no, just what we needed, a monkey wrench at 3 o'clock on a Friday. Well, it's not too bad because here's what they're going to do. Here's the scenario. The company wants to provide some kind of a guarantee to the customers. In other words, they're basically going to tell the customers, if your tires don't last at least X miles, we'll replace your tire for free. Fine. So what's the problem with that? Well, they don't want to be replacing all the tires they sell. They want to know what proportion of the tires are likely to be replaced. So let's say they're willing to accept up to 10% replacements. That means we need to figure out the correct number of miles that corresponds to the left 10% of this distribution. So in other words, here's the normal distribution again for the tires. And the mean is 36,500. X represents the number of miles such that 10% of the time, the number of miles is less than X. So think of it as the bottom 10% of this distribution. So we want to choose X to make sure that no more than 10% of our customers will require a replacement. Well, there's a couple of ways we can get to this point. We can start by calculating a z-score. And if we do that, let's come down here. We need to go to the normal distribution and say, well, listen, what is the cutoff point between the lower 10% and the upper 90%? How in the world do we do that? Well, what we do is we introduce a new function on the calculator. Aha, now this one is new. We haven't seen this before. So you go back to your calculator and you say, oh, I have not seen this before. On that same menu that we've been using, second vars, if you scroll down to number 3, you'll find the function INV norm, which means the inverse of the normal distribution. Wow. Now this one is a little different. And before we go any further, I just want to point out that not all the TI-84s are identical to each other. What I need you to do is look at your screen and see if you have area, the mean, the standard deviation, and this last part called tail. If you do, what I need you to do is make sure that it's set to left. Now, if it isn't, you can just move the arrow key and hit enter, and that'll take care of it. So we want that tail parameter to be left. Now, if your calculator doesn't show this at all, you're fine because the calculator is assuming that you want left. But when you have an option like this, we want to make sure that we're choosing left. So that way we're all doing the exact same thing. All right. Now unfortunately, you can't go down there and change it directly without doing the earlier numbers first. I don't think that's the way it works. You'll have to go and enter the other numbers. But when you get to the bottom, make sure it says tail is left, or else that it doesn't say tail at all. So you'll type in area of 10% because you're looking for the left 10% tail. You'll have a mean of 0 and standard deviation of 1 because it's the standard normal distribution. And when you get finished with all that, you'll notice that it gives you back a value of approximately negative 1.28. So what that's telling us is that whatever this value is, negative or 1.28 standard deviations below the mean is the boundary between the lower 10% of this distribution and the upper 90. Now, what we can do next is go back and revisit this formula we had before. This one. We're going to rearrange it algebraically and solve for x. Okay. So I've got that here somewhere. There it is. Since this statement is true, that algebraically, that means that x equals sigma z plus mu. Okay. So let's do that right here. So the z is the negative 128. And so if you plug those in, you'll see that you're going to get 30,100. Or in other words, think of it this way. The cutoff point between the lower and the upper 10, the lower 10% and the upper 90% occurs 1.28 standard deviations below the mean, which in this case with these numbers equals 30,100 miles. So that's what we're aiming for. So what we're saying is that the company should offer a guarantee that their tires will last at least 30,100 miles in order for them to achieve their goal, which is that no more than 10% of the customers need a tire replacement. I guess it was more than that. It could put them out of business. So they got to be careful here. They have to have a guarantee of some kind. Otherwise, nobody will buy the tires. But they don't want to overdo it either. They don't want to just say, well, anytime it wears out, bring it back. That wouldn't work either. Well, luckily, there's a quicker way of doing the same exact type of problem. Yeah, the simpler approach. We don't really need to use z-scores at all. What you could do is go to second vars, INV norm, use the area 0.10, use the original mean and standard deviation, and you'll see that the number you get is it's about the same. There's some rounding differences here, and that's because this 1.28 is only an approximation. So the two approaches will give us slightly different numbers. I'm not sure which one MindTap will ask for, but it's good that we know both of them. So it's going to be, any way you look at it, approximately 30,000, in this case, 92.24, just a tiny bit different than this one, 30,100. All right, so again, we're going to go through this again next time we meet with Excel, and then we can review the concepts at that time. But in the meantime, we want to at least take a peek at this next and final continuous distribution, which is the exponential. Now, this one is interesting because it's actually related to the Poisson distribution. So you might remember the Poisson distribution was used to determine the probability that a specific number of events occur over a given interval of time. Like, let's say we have a case where we know from experience that on average, 8 customers enter the store every hour. We can probably calculate the probability, for example, that 4 enter the store in the next hour. But what if our interest is different? We're not trying to figure out how many customers will come in the door during the next hour. What if instead we're trying to figure out the probability of a given time before the next customer shows up? Like, what if we want to know the probability that the next customer won't show up for another 20 minutes? Then we need the exponential distribution. All right. So Poisson is good for figuring out the number of events per time frame. This one is used for figuring out the time until the next event. So now we need a probability formula. Okay, so it's right here. And you'll notice a lot of familiar elements. For example, the mu is our mean. This is the same mean that we used in the Poisson distribution. As you know, E is approximately 2.71828. We saw that also in the Poisson distribution. So let's use that same example before a customer is coming into the store. If I told you that the average number per hour is 8, I could ask a question like this. What's the probability that the time until the next customer showing up is somewhere between 10 and 15 minutes? Okay. And by the way, I just want to remind you that with a continuous distribution, we can only calculate probabilities for intervals. Probabilities for single values, like over here, are automatically equal to 0. So we're always using intervals. And so now the only thing is we have to watch out for is this. If you notice, the mean is defined in terms of 8 customers per hour. This is in terms of minutes. So here's what we'd have to do to answer this question. We'd have to change it from 10 and 15 minutes to 1/6 of an hour up to 1/4 of an hour to be consistent with the mu. So that we'll discuss when we start doing these problems. So anyway, this is more or less where I left off of the other classes. I decided that I didn't want to push it too far, especially because so many people are not here. So at least now we're really completely done with our discussion of the normal distribution, except for the Excel. The exponential will have to start all over again next time anyway. So I think it makes sense that we could stop right here. So as like I said, I'll be posting the video in this document so you can read them later on and watch the video if you want. And then in the meantime, your job is to have a fun time on spring break. And I'll see you all a week from Tuesday in the classroom. All right.
Thank you, Professor. Have a good break.
All right, you too. Bye.
Thank you.
Thank you.
Later. Okay, bye.